Okay, welcome to the live interactive session for the NPTEL course Advanced Transition Metal Organometallic Chemistry from Principle to Application. So this course, in this session, we are mainly discussing 10 to 11 problems regarding the weak content. So currently our course third week is going on, and as a TA for this course I am hosting this session in every Tuesday from 6 to 8 p.m. from 6 to 8 p.m. So I will wait for some time, then I will to for joining the people, then I will start discussing the today week content, that is the content of this week 3. Then I will uh, solve some sample question to describe the weak content through the problem solving approach. I will wait for another 5 minutes or 6 minutes for joining the people, then I will start discussing the questions. I will wait for a few minutes, then I will start discussing I will wait for a few minutes, then I will start discussing this week content through this problem solving session. I will wait for another 2 minutes, then I will start discussing today's session. Okay, who have joined? I think one people have joined. Do you have any doubt regarding this course or this session? Okay, so let's start today's session. Welcome again to the NPTEL course Transition Metal Organometallic Chemistry Principle to Application. So in this session I am hosting this session as a TA for solving the different questions, that is as a sample question for from this week content, for the better understanding the weak content and mainly the approach to solve the question to find out the current answer. So if you have any doubt regarding this session, you can directly ask me in this live session, that is every Tuesday from 6 to 8 p.m. And if you have any doubt regarding the lectures taught by the professor, you can just post your doubt in the discussion forum. So till now we did not get any question in the discussion forum. If you have any doubt, I encourage everyone, so any kind of doubt regarding the course content and the lectures and the slides, please post your doubt in the discussion forum so that you understand the course or the content of this course more deeply, and you which will help you to solve the assignment problem as well as the problems from the exam. Not only in this exam, also other different competitive exams based on this chapter, transition metal or organometallic chemistry, principle to application. So without wasting time, let's start today's session. So this is a week 3 content, that is we have covered 5 lecture from lecture 11 to lecture 15. So start in the last, so I will just recap the last week content quickly and then I will discuss this week content. So in the last week we have discussed the different classes of organometallic compound, and we have seen how they are classified in class 1, 2 and 3 depending on the electrons, that is the total valence electron it had. Also we have seen how the molecular orbital and the energy diagram differentiate the three classes of the compound. And later on we have seen that the preparation and the some introduction to the oxidative addition reaction to this organometallic compound. In the end of this last week content, we start moving ourselves to the properties of this organometallic compound, mainly the organometallic sigma alkyl compound. Alkyl compounds are generally not so stable in the normal condition, but with the modifying electronically and sterically around the metal center, there are so many complexes which are also stable in normal condition. So the transition metal alkyl or aryl complexes, their synthesis is we have already discussed. So now in this week we have discussed the properties of this transition metal sigma alkyl complexes, and in properties we have mainly discussed the stability of the metal alkyl complexes, in what condition they are stable and what condition they are not, and also in terms of stability we introduce a term beta hydride elimination or beta hydrogen elimination. Beta hydrogen elimination for transition metal alkyl complexes is a main or major way for their instability or their decomposition. After getting this, we also read the three possible way how to get rid of this beta hydrogen elimination step which gives the instability to the system, that is how to suppress the beta hydrogen elimination to have the stable complexes. And at the end of this we have came to know that some complexes having beta hydrogen, they are also stable because of the steric and electronic demand. And it is the last lecture, that is the 14 or 15, we have seen on the importance or application of the transition metal sigma allyl complexes in their catalysis. We have just started at the end of this week content. So without wasting time, let's directly move to the today's first question, which is the primary mode of possible decomposition pathway in sigma alkyl organometallic compound is or are. So sigma alkyl compounds means the transition an alkyl group bonded to the metal. That is, we have our alkyl group like M bonded to any alkyl group, let's say R. So if this R contained a beta hydrogen like M CH2 CH3, then this beta hydrogen, this is alpha, this is beta, this beta hydrogen over this carbon atom is highly susceptible to donated by the metal center to a 4-member cyclic transition state. So for this, that's why the elimination to give the alene. So to give the olefins. So metal we have CH2, then we can write CH, CH3. Then this transition step is happening over here depending on the steric and electronic demand on the metal center. So metal will extract this hydrogen as a hydride to leaving the system to leaving as a olefin. So we have our metal hydride and plus to leave this as a olefin. This mode of reaction for metal alkyl complexes is very much familiar or very much uh, susceptible for this. So 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 the common or primary mode or decomposition pathway for the sigma alkyl complexes is the beta elimination. So here our option B will be correct answer. Going to the next question is the way to suppress the beta elimination pathway in sigma alkyl organometallic compounds is or are. So, as we seen that for the metal alkyl complexes, these complexes are very much susceptible to undergo the beta hydrogen elimination reaction. That's why metal alkyl complexes are very unstable, that is highly reactive in nature. Even they decomposes at very lower temperature like minus 40 or minus 50 degrees centigrade. So now we have our question in mind that how to suppress this beta hydride elimination reaction to get the stable metal alkyl complexes. For that we have our second question. The way, that is ways to suppress the beta elimination pathway in sigma alkyl organometallic compound is or are. Here option E is central metal atom should be coordinatively unsaturated, and then option B, anyone know the answer?
Absolutely.
Answer B. Hello, what will be the
Yes, sir.
correct answer?
Answer C.
Answer C. Okay, you can mute yourself. Answer C here is the correct answer. So when we are discussing the beta elimination pathway, that means the elimination of beta hydrogen. So if the system doesn't contain any beta hydrogen, that is no need or no way to undergo the beta hydrogen elimination. So the only, not only the one way, one way to suppress this beta elimination is the system should not have any beta hydrogen. For example, if we have metal CH3, that is organomethyl complexes, that is also a sigma alkyl complexes, we have only alpha hydrogen, there is no beta hydrogen. No beta hydrogen. So we can easily say that some complexes without beta hydrogen is generally stable. We have our another example like M CH2 CH3 CH3 CH3. These also does not, this is alpha and this is beta. So this also doesn't have any beta hydrogen. So that's why these complexes may be stable or may not undergo the decomposition through the beta elimination step. So here we got our answer to option C. Our third question is identify the ligand with beta hydrogen atom. Option A is simply a alkane chain. Option B is only methyl. C is something with the silicon compound, and D is the benzyl group. So the beta the question is identify the ligand with beta hydrogen atom. So as we have already said in the previous question that beta hydrogen is when it is attached to a metal like R, and that R will count the electron as CH2 CH2 CH3 like attached to the metal. So the first carbon attached to the metal we call it an alpha, then beta. So here we can see only this is alpha, this is beta. So only option A has the beta hydrogen. That means option A will be the correct answer. So here only the methyl group, there is no second carbon atom to have the beta hydrogen. For the option C, this is alpha and this is silicon. So these also doesn't have any hydrogen over here. That is also no beta hydrogen. And for the benzyl ligand, so this is alpha and this phenyl ring is the aromatic ring, also does not have a beta hydrogen. So this does not contain any hydrogen. So here option number A will be right answer. Going to the question number 4, that is the between TiCH2 CH3 whole thrice whole 4 and Ti titanium CH3 whole 4. So which one is, here we are considering the stability of the both the complexes. So here we have our Ti, this group we called them as a neopentyl ligand. Neopentyl ligand. So it has the structure CH2 C CH3 CH3 CH3. This is attached to the titanium, and we have this total 4, whereas titanium has only CH3 4. So as we have seen that both the complexes, that is titanium complexes, doesn't have the beta hydrogen. Here only one hydrogen is there, this is alpha. Another one we have alpha and beta, but the beta carbon atom does not contain any hydrogen. So ideally, so both the complexes should stable, but we have seen that due to the unsaturation, that is the coordinative unsaturation of these titanium tetramethyl complexes is very much reactive, and because it has the coordination unsaturation because of this small methyl group, and it is 4. So for the transition metal complexes, we have seen that general coordination number for the transition metal is 6. So we have another vacant place to occupied by this titanium. It undergo the decomposition in a binary pathway. We will discuss that later. So here, due to the presence of a very bulky substituent, the around the titanium, these complexes are very much stable. Even its melting point is solid, and melting point is around 90 degree. Whereas for these tetramethyl titanium complexes even decomposes minus 40 degree centigrade. So as we have seen that or we have told that some complexes are extremely unstable even at very low temperature. So here the correct answer will be the titanium neopentyl with the neopentyl ligand is more stable than the titanium tetramethyl complexes. So here option A will be correct answer. So then we can see how these undergo the titanium tetramethyl complexes to decompose in normal temperature. So generally the titanium tetramethyl complexes decomposes via a bimolecular mechanism. So here we have our 3 methyl group like Me3 titanium, we have our 1CH3 here, and then 1CH3 here attached to the another titanium. So here there is an interaction between these two molecule of tetramethyl titanium. So here this bonding of titanium methyl titanium is like not two center two electron bond, but it is a instead of two center two electron bond, this titanium methyl titanium is generally a two center a three center two electron bond. For that, like titanium carbon titanium, so for this bonding method, it weakens the titanium carbon bond, and that's why it decomposes very rapidly even at very low temperature minus 40 degree. So our option will be option A. The next question, that is the question number 5, is the tetrabenzyl zirconium with the tetramethyl zirconium. Then again the stability of these two complexes. So question is the tetrabenzyl ligand zirconium is more stable, less stable, or both are stable, or has the beta hydrogen atom. So we so Can anybody know the answer? You can tell me.
That will be option A.
Okay. Yes. Why option A is correct?
So because the first one is coordinatively stable, coordinately saturated.
Yes. But coordinatically saturated we are considering with the coordination number. Here both have 4 coordination number. You can see. Then how you can say it is saturated? Both have 4, na? Both the zirconium complexes have 4 ligand. Methyl also 4, benzyl also 4. Yes, your answer is correct. Option A is more stable. That is zirconium benzyl is more stable than zirconium methyl. And you point out the term coordinate coordinatively saturated. Now I have said in previous questions that coordinative saturation with respect to coordination number 6. If it is less than 6, we can say that it is coordinatically unsaturated, because most of the transition metal in the first row generally or higher is show the 6 coordination number, that is most preferable. But if you have some very big ligand like benzyl, okay, then in the previous we have seen that this is neopentyl, so that big ligand around the metal center is covered more space than this small ligand like the methyl. So because of the steric bulk of the benzyl ligand, it doesn't allow to come other benzyl moiety to bond with the zirconium. That's why we can say somehow it is because of this large size is coordination we are restricting to coordination number 4. So that's why the another reason to stabilize the zirconium benzyl tetrabenzyl complexes. Is this clear?
So
Okay. Okay. Because of the large size, it doesn't allow other ligand to come like that tetramethyl I have shown for the titanium. This binary mechanism for the decomposition. So this binary mechanism, if you have very large or bulky ligand, it will not possible to come together to form this 3 center 2 electron bond to have this weakening the metal carbon bond or metal alkyl bond. That's why this system become highly stable. Okay, so option A is the correct answer. Next question is between titanium CH4 and lead CH4. Again the stability, because in this week we are mainly discussing the properties stability of the transition metal complexes, transition metal alkyl complexes. So stability in terms of beta hydrogen elimination we have already discussed through this problem solving. Now both the metal complexes have 4 coordination and both have the small ligand like the methyl ligand. Now how you justify the stability of these titanium versus lead tetramethyl complexes, and tell me what is the correct answer.
by using the energy of d orbital in titanium and lead.
So what will be the correct answer?
B.
1 minute. Okay, so titanium tetramethyl titanium is less stable compared to the lead. Why? Yes, option B is correct.
So due to the energy of d orbitals, the higher energy of d orbitals.
Yeah, higher energy obviously titanium in 3D group, whereas lead in which group? 5D, 5D6s. Okay, so higher energy obviously the energy is higher, orbital are big in size. How the higher energy affects here? Option is correct, answer is correct. Okay, so see titanium in 3D group, whereas carbon in 2D group. 2D is not existing, 2p group. So the bond energy differences, that is the energy differences, is not that much. So it can easily form the this one, this two, this bimolecular structure. That is the 3 center 2 electron bonds with the interacting with the methyl group with the other titanium molecule. Okay, but if we have like this lead which has very bigger orbital, so carbon cannot interact with the other molecule of this. That's why this bimolecular decomposition pathway for this is not favorable, which is favorable for the titanium because of the higher energy difference. Higher energy difference between the carbon atom and the titanium, and then carbon atom and the lead. So uh, that bimolecular pathway is not favorable. That's why this is another stable. Also, we have seen that beta hydride elimination, and both the complexes doesn't contain any beta hydrogen atom. That's why we cannot consider the stability in with the beta hydrogen. So only thing is that stability of these complexes with the energy difference between the orbitals. So carbon has 2p orbitals, titanium had 3d orbital. The energy difference between these two is small. So the one methyl group from one titanium tetramethyl complex can interact with the another titanium center to form this 3 center 2 electron bond, whereas the lead is maybe 5d6s, so the energy difference is huge. So it cannot it cannot interact carbon with the another another molecule, all another molecule. So this bimolecular decomposition mechanism is not possible. Also, that layer, the d orbital is filled. Okay, so only vacant is the p orbital, but for the titanium, CD orbital is vacant. So titanium is a transition metal and it has a D2 system. D2 system. So for the D2, it has another only 2 electron is there. So another 3 electron is vacant. So it can extend its um, or it can accommodate more electron from electron density from the methyl to accommodate here. That is not possible for the lead also. That's why this interaction is favored in bimolecular interaction is favored in titanium tetramethyl complex, which is not favored in lead. That's why it decomposes by this mechanism, whereas lead is not decomposes in the mm, and bimolecular mechanism, and that's why it is stable. So 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 lead tetramethyl complex is more stable than titanium. The next question is the decomposition of the type proceeds via. This I have already explained. Now it will be the right answer.
A biomolecular pathway involving 2 electron 3 electron bonding.
Yes. So the decomposition of the tetramethyl titanium proceeds via a bimolecular pathway involving the two center 3 electron bonding. Here it is written something wrong. It is 2 electron. It's, yeah, 2 center 3 electron. A 3 center 2 electron 3 center or 3 center 2 electron is the same. This is the 2 electron and 3 center. 3 center is titanium carbon titanium and 2 electron bonding. So this is the decomposition of option C will be correct. Okay, this question is related to the previous question. So if titanium tetramethyl complexes is highly decomposes, then what is the possible way to stabilize this? A bimolecular decomposition pathway is not possible in biopyridine TiCH3 because the titanium center being here. What will be the correct answer?
So it will be coordinatively saturated due to the chelation effect of bipyridine.
Yes. So we have seen that the titanium tetramethyl coordinatically saturated due to the chelation from this biopyridine. Very good. So we have seen that the titanium CH34 undergo decomposition in a bimolecular pathway through the 2, 2 electron 3 center bonding model. But if we add bipyridine with this system, its coordination number, that is coordinatically unsaturated, that is the 4, with respect to the octahedral coordination, that is 6. So if we increase or if we add a bipyridine, the bipyridine structure is, so we have pyridine.
Pyridine connected through a bridge bond.
Is this correct?
Sir, it will be in opposite positions. The nitrogen will be.
Nitrogen will be opposite position.
So 4, 4 bipyridine.
That you are saying that here it will connect, huh? You are saying like this. Like this.
Sir, yes, sir.
You are saying like this, right?
Yes, sir.
So which, okay, then I have a question. This is also correct, this is also correct. We have bipyridine. So for this system, just tell me which should I use to stabilize, that is which bipyridine should I use, this molecule, molecule A, or molecule B? Just think.
Molecule A.
Why molecule A, not B?
Because we have to coordinate it. This is bulky group, so 2 nitrogen comes in the same side that we can coordinate it.
Yes.
So
So you got your answer right. So if we have, this is called 2 dash bipyridine. This is will be someone 4 dash. So if we have our metal over here, so it will coordinate like this to the metal center. So if we have 4 dash, it one bipyridine molecule should coordinate two metal center. For that our coordination requirement, that is the, we should increase our coordination from 4 to 6, will not satisfy. So this bipyridine will be 2,2 bipyridine, not this 4,4 bipyridine. So 2,2 bipyridine we will use to just increase the coordination number 4 to 6 to generate the coordinative saturated molecule to stabilize this titanium tetramethyl complex. Is this clear?
Yes, sir.
Okay, you got your answer? You got your answer, right?
Yes, sir.
Okay.
Yes, sir.
Do you have any other doubt? Do you have any other doubt?
No, sir.
Okay. Then I will proceed to the next question. This is another question. This is again titanium tetramethyl with the trans 10 hexamethyl complexes. Again the stability of the both the complexes. The titanium tetramethyl is more stable than hexamethyl trans 10, or it is less stable, both are stable, or it has beta hydrogen atom. So obviously as methyl is there, so there should not be any beta hydrogen. So just cut out option D.
Option B.
This is less stable than tungsten hexamethyl. Okay, so this, as I say, just mention that cut out option D. So this is the one of the approach to solve the MCQ or MSQ type question. When you solve MCQ or MSQ type question, you may not know all the answer, but you may have some information about the question. By the using that information, that is here we are considering the stability of the transition metal alkyl complexes. So the one possible mechanism for decomposition of the transition metal is the beta hydrogen elimination. So here when we are considering if it has beta hydrogen, it will be decomposed faster, but here we have seen that both doesn't have any beta hydrogen. So beta hydrogen option, that is the titanium tetramethyl had beta hydrogen atom, we can easily delete this or cut out this option. So our three option is remaining. So when we are considering the stability of the two complexes, mostly the one may be the stable, another may be the unstable, because here we have also know that stability depends on the coordination number. So here tungsten hexamethyl complexes has the coordination number 6. Where it is 4, we have used the bipyridine to stabilize this system. And what is the structure of this tungsten hexacarbonyl? Is this octahedral? Is this octahedral?
Big.
What? If we use the VSEPR theory, it will lead to us wrong information about the geometry of these tungsten complexes. But these hexamethyl complexes have a very in general structure, like it has trigonal prismatic structure. Any idea? Do you have any idea about this trigonal prismatic structure? Also this question is very familiar if you go the previous year question of net and gate. This question is very familiar. The structure and the coordination number of tungsten hexamethyl. Or you have the another D0 species which have the same structure like tantalum CH3 whole 6 minus. Also the zirconium CH3 whole 6 minus. These all have the D0 complexes and have the zirconium 2 minus, and all have the trigonal prismatic structure. So this is a very common question. You just see what is the structure. So trigonal prismatic means we have one trigonal and this will form a prism. It is not looking good in this way, so we can write it like this. So here all the methyl group is here 6 position, this 3, and zirconium is stay on the middle. Now I think this prism is understandable. This is not possible to understand. So this is the hexamethyl titanium, hexamethyl tungsten. Sorry, this is hexamethyl tungsten. Hexamethyl tungsten structure for this. This is a trigonal prismatic structure. Okay, and the last question for today's discussion is the reason for tungsten hexamethyl complex being more stable is due to the tungsten center being what will be the correct answer for this?
Coordinatively saturated.
Yes. So it is coordinatically saturated. Does it have only one correct answer? Look other options also. It has more than one option correct.
Electronically saturated.
You are saying electronically saturated. You are saying this electronically saturated. So tungsten complex is electronically as well as coordinatically saturated. That's why it is stable. But just I have discussed many complexes with the valence electron count. Just you count the valence electron of WCH3 whole 6. What will be the valence electron count for this complex? We have said that it is electronically saturated. Electronically saturated means it should have valence electron 18. Okay. So what will be the total valence electron? Tungsten in which group?
It will be 12.
Tungsten in which group? This is in chromium group. Chromium, molybdenum, tungsten. So chromium has, or this group has electronic distribution D. What is the distribution for chromium group?
D4
D4
6s.
S.
2.
D5S1.
Huh? Another option D.
5S1, sir.
D5S1. Why it is D5S1 or D4S2? Which one is correct?
D5S1 is correct, sir. Due to half-filled orbital having stability.
Because of this half-filled d orbital always should have the electronic configuration d5s1, not d4s2, because d4 is just before the half fill. So d4 is just before the half filled, so the electronic configuration will be d5s1. So this will have 6 electron plus methyl will have 6 electron. Total electron will be 12. So is this electronically saturated?
No.
No, sir.
And then without electronic valence electron calculation, how you can say it is not electronically saturated? So this is electronically unsaturated. So the option A will be the correct answer, not option C. Okay, you got the point, right? Sometimes mesh table does not lead to the electronic saturation or coordinating saturation. We have seen a first question with the benzyl ligand, a neopentyl ligand. Neopentyl ligand has 4 ligand. Also the tetramethyl has 4. So you can say both have 4 ligand. Why it is coordinatingly saturated? Neopentyl one, but not the methyl one. Both have 4 ligand. But we are considering the electronic saturation with respect to 6. So both are coordinatingly unsaturated. But I am saying this is coordinatingly saturated because of this large size. So then the same thing appearing for here also. Without electronic calculation, don't say this is coordinatingly or electronically saturated. It has 6 valence electron for transition metal complexes. General valence electron count is 6, so 6 is okay. So you can have an idea that it may not go, if you go beyond 6 it may be unstable or because of this transition metal. And but when you are considering electronic unsaturation, you should have always calculate the electron count, or that is the valence electron count for these complexes. This only you can say that electronic saturation or unsaturation. Is this clear?
Okay, sir.
Do you have any other question?
No, sir.
Anyone?
So can you explain about the bimolecular pathway?
Bimolecular pathway, okay. Thank you. So bimolecular pathway, this is the bimolecular pathway, and this is well differentiate with this question between the yes. So here we have same ligand, that is the methyl, both the cases, and we have our coordination number 4, that is fixed for both the complexes. But one is, that is the lead is stable, whereas titanium is not stable. Why? See, the titanium is a 3D element, whereas if you consider lead, it is in 5D 6s group, right? Where you have the methyl group is same for both the system, it is 2p. When you are interacting this system for the titanium methyl interaction with the methyl group with one titanium attached to the one titanium is able to interact with the other titanium because of this the closest energy between the two orbital. But for the lead, whereas the interaction with the 2p with this 5d and 6s outer orbital is not that much facile. That's why these molecules easily undergo the decomposition, like the 1-methylene interacting with the other titanium molecule. Because of this interaction, it is able to form the 3-center 2-electron bond. That is, the electron density of one titanium methyl bond is shared with to interact with the same methyl with the other titanium atom. That's why these 2 electron is also sharing the bonding with the other titanium atom in a 3-center 2-electron fashion. As this bonding electron of these, the methyl attached to the titanium is using to interact the, the methyl atom to the other titanium atom. That's why this bonding of methyl with titanium is weakened. Okay, that's why, and the same thing also happening the methyl attached to the other titanium. Because of the formation of 3-center 2-electron type bonding, this titanium methyl bond gets weakened. This is simple, and that's why this complex become very much unstable. Even as minus 40 degree, it is a very low temperature, it also decomposes. But these types of interaction is not possible in case of lead, because it is in heavier main group element and it have very large orbital 5d 6s, and energy gap between the 2p and 6s to interact with the other molecule is very high. So this 2p electron, it can bond with the palladium, but it is very difficult to form the lead. Pb is not Pd. So another lead to come into the picture to interact with the another lead molecule to interact. Okay, so that's why this bond, that is a methyl group, is not able to interact with the another lead molecule, another lead center. That's why the electron density totally remain in this methyl bond, that is the lead methyl bond. That's why it is stable. Main thing is the 3-center 2-electron bond formation is possible in titanium tetramethyl complexes, which is not possible for the heavier congeners like the lead, because of the large energy difference between the two orbitals. That's why it gets stabilized. You got the point, right?
Yes, sir.
Any other doubt? Any doubt regarding this? So we have our sigma alkyl complexes. So we have our 3 criteria by which these complexes we can stabilize these complexes. What are these 3 criteria? So 3 ways or 3 criteria to stabilize the metal or transition metal sigma alkyl complexes. We have 3 OS or 3 criteria. What are they? We have discussed in today's series how to suppress the stability. This is decomposes mainly due to beta hydrogen elimination. Okay, so we have our 3 criteria in our hand so that we can suppress the beta hydride elimination pathway. What are they? Can anyone? Okay, if not, then I will discuss. Okay, three ways. So one way is that metal should not have this metal sigma bond should without beta hydrogen. If it does not have any beta hydrogen, it will does not undergo the beta elimination pathway. Second criteria is the it should be coordinatively saturated. It should be coordinatively saturated. So if it is saturated, these types of transition state is not possible because metal cannot increase its coordination number to interact with this beta hydrogen. This is the second criteria, and third criteria is electronically saturated. But this criteria is sometimes may not valid. So main two criteria is the and another criteria can be that the olefin formation, the olefin which are forming is not stable or energetically favorable. Then this condition is to 3 OS to stabilize the transition metal alkyl complexes to prevent or suppress the beta hydride elimination. Okay, another thing is that if we have our beta hydrogen, so let's say we have an example which have the beta hydrogen but it is also stable. This is for the like norbornyl group. What is that? It is like somehow like this. If we have a metal attached to this and we have this 4 ligand attached to the metal, so after beta hydride elimination it will be someone so that or here. So the double bond in either of the bridgehead position here or here is not stable, which is called the Brett's rule. So these types of system, instead of having beta hydrogen, they are not undergo the beta hydrogen elimination process. Another thing is that there are some complexes which have the beta hydrogen but they are also stable, that means inert. So we have, that is, we can say that exception of this beta hydrogen elimination. We have complexes or the rhodium complexes like NH3 whole 5, RH, C2, H5, two plus. So these complexes have C2H5 group, that is mainly a CH2 CH3 group which attached to the metal like rhodium. It has alpha and beta hydrogen, but this complex is kinetically very much inert. So this is, we can say, another type of exception to stabilize stable organometallic complexes, organometallic sigma allyl complexes which have beta hydrogen but it is stable. if we have our organelles, that is organoalkyl complexes with the higher congeners like 4, 4D, 5D metal, as per example rhenium CH3, this. So these organorhenium complexes is highly stable because, as I discussed for the lead, these organorhenium complexes with the methyl group, having the methyl group, is highly stable in nature. So when we are discussing the unstable uh, organo sigma alkyl complexes, we should also remember some stable organo mm, alkyl complexes, that is the metal alkyl complexes. So now we can move to ourselves the application of organometallic, that is the mainly the organoallyl alkyl complexes to the application process. So for the application, we have last day we have discussed the application for, we have discussed one topic, that is the oxidative addition topic. So the organo transition metal sigma alkyl complexes generally applicable in different types of, applicable in the CH activation reaction, that is the conversion of hydrocarbon to generate the industrially value added chemicals. For that we use these organo metal alkyl sigma alkyl complexes as catalyst to generate or to activate the CH bond to convert the hydrocarbon, which is a natural product, natural hydrocarbon, natural petroleum product, to different value added product. That is, for example, if we have our alkane like CH4, if we can convert it to using CO, we can convert it to CH3 COOH or CH3 COO CHO, that is the aldehyde, that will further conversion to give the value added product. For that CH bond we need to activate, that is the functionalize CH bond. Functionalization of CH bond is thermodynamically highly unfavored because of the high bond energy. But if we have our HH bond, we can easily activate this bond using the our any metal alkyl complexes to give the metal hydride, because the hydride formation is energetically favor delta H 0, whereas if we have metal plus CH, this will give the metal, this is highly unfavored because of this delta H greater than 0. So or delta H equal to 0. But with the help of these complexes we can done this conversion easily. So that is the CH activation reaction. CH activation is mainly functionalize the CH bond to other, in CH bond in alkenes or hydrocarbons, to give the value added product. So today with the last example I will discuss the intramolecular CH activation. Intermolecular CH activation. For that we have our complex, like let's take for example iridium Cl P pH3 pH3 pH3P. Here the oxidation state of iridium is +1. So here we have the 3 phenyl ring attached to all the 3 phosphine groups. So here using this iridium catalyst, that is the iridium metal, we can activate the the carbon atom from the one of the phenyl ring to go the another product like this. We have converted this iridium 3 and its coordination number will also increase. This is called the oxidative addition pathway. Here we have our 1p pH2 and with our another pH ring is undergo the activation to give this. Another pH3 will remain same. So this is the activation of this CH bond of one of the phenyl group to undergo the give the sigma alkyl complexes. So when this group is activated, we can further modify this to different value added products. In next lecture or next series, we will discuss this CH activation reaction in more details. It is the preliminary idea how this we can convert that hydrocarbons or generally the alkenes or alkynes to value added product for our day to day life. And for that transition metal complexes are very much useful or to do this job. Any other has any question?
No, sir.
Do you have any question regarding the lectures?
No, sir.
Did you fill the form for the registration for the exam?
Yes, sir. I completed the registration, sir.
When the exam is there? Which date?
So it will be 26, I think, sir.
Okay. So this year exam will be very difficult, I can say this. So exam questions are not easy. So try to. And what is the exam registration now? How many people register for the exam? Do you check that?
Sir, no, sir.
Anybody? Anyone else? Do you need any other kind of help which I can do instead of doing like this question solving? Because this session is mainly to help the student who have done this registration and to clear their doubts. Okay, so it is better if you have any doubt, any other doubt regarding this chemistry, not only this course, other thing also mainly with this course. This session is for that doubt clearing session. Okay, so if you have any doubt regarding the course content or where to read, how much extent you can read, I can help you. So
So in the exam point of view, the problems will be based on the lectures or
yes,
more than the lectures.
no, actually from the exam point of view, everything will be on the lectures, but the assignment question you follow it thoroughly, also follow whatever the question I am solving, and I can say that it will be mostly on the lectures, maybe 80% on the lecture. That will, if you cover all the lectures with proper note and all, you will get good marks, that's for sure. Okay,
Okay, sir.
if you want to read books, then here in that, actually in, I think lecture 1 they have mentioned 2 books. Okay, one book is Captree, which is very difficult to read, so I suggest you to read the Christopher Elson Boyce for organometallic chemistry. Most of the questions or slides whatever you have seen is based on these books. So please, it is also mentioned in the, I think, starting of this course, starting one first lecture.
Yes, sir.
So you can download that book, or if you want, then I will also upload in my slide folder. You are getting this slide, right?
Yes, sir.
Okay, this is just the question. So if you need it, I will also upload the books, but that is not good. You better download it. Huh? Christopher Elson Boyce, you will find all the slide content, and you can read thoroughly, not going by the lecture but by the book also. Okay,
Yes, sir.
and cover the content which has been taught till now, so, so that you can uh, qualify the exam well. Because from my last year experience, this very few people got qualified in the exam. So, so I better to ask question here. Huh? Better to ask question in this live session, in this discussion forum, any kind of doubt. If you have whatever the question pattern, whatever the this, if you have any kind of doubt, you can just post your queries regarding this course lecture videos or course content which is being taught, so that you will have a fair idea about this course and you will get a good marks in the exam. Okay.
Okay, sir.
So exam is 26. It's a lots of lecture. Only 15 lecture has been covered. Total 60 lecture is there. So remaining 45 lecture is remaining. That's a lot. Even if you see as the course move on forward, some very interesting topics we are going to cover in this introduction. That is the principles to application course, like CH bond activation, then CC bond activation, how the orbital of carbon interact, also metal, that is different kind of activation, like carbon CH activation will just start in the last lecture, will continue in the next week. And any other suggestion to me so that I can improve my session for your help.
Sir, can you discuss the problems other than the professor discussed in the lecture, sir? Like extra problems
Extra
or
problem.
other questions or for homework or like that something?
No, actually I am not allowed to give any homework or something like that. Whatever I have, I will show you in the slide. You take your time, 2 minutes, 3 minutes, 5 minutes. You just tell me the answer and then I will discuss. Okay, one thing you are telling me, you should I increase the more number of question, right?
Yes, sir.
I am restricting myself to 10. You are asking me to increase more, like 20, 25.
Yeah, maybe, sir.
Okay, okay. That will try. I'll definitely try to increase from the next session to give the more topic, or as you are saying that topic which is not covered by the professor, that is I think don't require, because in the exam most of the question will be asked from this topic whatever taught by the professor. Not a single question will be from the outside of the lecture. Okay, so it is better for you to restrict in the topic, not go beyond that for this exam. If you want to learn me, if you want to learn something else, something outside of this topic, you just tell me today, I will discuss it in the tomorrow, that is the next session, if you want to learn.
So,
Okay,
yes, sir.
like if you want to learn any other topic related to this organometallic chemistry, mm, if you want to, then I will discuss in the next. If you tell me today, then I will prepare for that, and the next day at the end many people will leave, huh? So at the end, after when we finish the question, many will, then we can discuss according to your requirement. Okay, so this course is a long course, 60 lectures, and slides is almost 400 450 slides is there. So this slide, that is the question I will share, but I can't share the original slide. So original slide you have to note down from the lectures. Okay, so this is all for today. I hope you will enjoy the session, and if you want to know anything outside the topic, but that should be related to this topic, that means organometallic chemistry, not other than organometallic chemistry,
Yes,
that
sure.
then you can ask me. If you tell me today, then tomorrow I will discuss it, because I need time to prepare it well, so that I can tell you in detail. Okay. Okay,
Okay, sir.
anything else, any other doubt?
No, sir.
Okay, thank you.
Thank you, sir.
So okay, today I have discussed the 10 example or 10 questions, and I have shown how to solve them. Hope this will help you, whoever will watch this session in offline, that is not in live mode, but I ask everyone to join in this session and get your doubt cleared. If you cannot join the session, just post your doubts in the discussion forum. Discussion forum is where open 24/7. Just post your doubt in the discussion forum, so that we will quickly pick up the question and we will try to solve them as early as possible, and we will post the answer quickly. So again, thank you all for watching this session, and I am hosting this session for clearing your doubts on every Tuesday from 6 to 8 p.m. as a TA for this course. So from the next day onward, as I suggested, I will try to increase the number of questions from 10 to some higher number for the help of the students. Also, I will elaborate the topic in more detail. So better is, I will ask you everyone to post your doubt in the discussion forum and get your doubt cleared. I will wait for few minutes if anybody wants to join, otherwise I will stop the session after few minutes. I will wait for another 5 to 10 minutes if anybody wants to join. Otherwise, I will after that I will close this session. Do you have any question? Do you have any question? This session I have started from 6 p.m. and it is about to end now. If you have any question regarding this, you can ask me. Can you hear me? If you have any question regarding this course content of this week, that is week 3, if you can ask me. Okay, then please try to join on 6 p.m. when I have started this session, because I am just waiting for someone if anybody joins. So I have, in this session I am mainly discussing some sample problems and the approach how to solve them. By doing this problem solving session, I will also clear the doubts if you have any during this 2-hour session, that is 6 to 8 p.m. So today's discussion is already over. You can directly watch it through the YouTube. I will upload it shortly. Or from next day onward, that is from every Tuesday during this course, please try to join on 6 p.m. to get your doubt cleared. If you have any doubt regarding this, you can ask me now also. Try to join from next session Tuesday 6 to 8 from 6 p.m. Okay, and if you have any doubt, you can ask me now, or you can post your doubt on the discussion forum, and we will try to resolve your doubt as quickly as possible. Is this clear? Okay, now I have already done this session for today. You can see this session in from the YouTube and through this Google Sheet link, and from next day onward try to be joined from 6 p.m. Okay, thank you. Now I have done the discussion for today's session. If not, I ask you or request you to join from the next Tuesday live session. Or if you have any doubt, you can just post your doubt in the discussion forum regarding the exam pattern, content, anything, anything you have, like the slide, whatever taught by the professor. Okay. If not, then you watch today's session from the recorded video, week 3 recorded video, and from the next day onward, that is the next Tuesday from 6 p.m. you join in the live session and see the recorded, see the live discussion. If you have any doubt, you just ask me. I will try to clear your doubt as much as detail as I can. Okay. Okay, then I will close this session. From next day onward, I will hope I will see you in the live session from 6 p.m. every Tuesday. Okay, thank you. I am closing this session. You can leave.